Hi everyone, my name is Mike Ulrich. I work at Google. I'm a site reliability engineer, or SRE. Before I get into really what that is, I'll give you a little bit of background about myself. I used to be a chemical engineer. I used to study chemical engineering. And chemical engineering is really this practice of like taking something that maybe a chemist comes up with and engineering it to work at a large scale. So like, you might have done some lab work in chemistry in maybe high school or college or something, and you take A and you take B, and maybe some bubbles come out or something like that, and maybe there's a little bit of heat. Those bubbles that come out might actually produce a lot of gas, and this gas could actually cause a plant to explode or something like that if you're not careful. The heat that a reaction produces might cause a big problem at scale. And site reliability engineering is sort of like taking these small problems that might exist, at kind of a microcosm at like an individual server level, and understanding it in a bigger picture, understanding how like systems work together and what can sort of break. So like what I sort of studied in chemical engineering is process flow diagrams, and there are like these individual components like these separator towers and heat exchangers and so forth that you sort of need to understand at like the microscopic level, at these like individual component levels. And then you need to understand the whole network of it, right? All of these pipes are connecting these different systems, and what can happen if this thing gets a little slow, what happens to the rest of the system. And this is kind of what I look at today. I look at a system that looks something like this, right? I have caching layers and proxies and front ends and storage layers, and they all have different behaviors and different failure modes. And you kind of need to understand how all of these different systems work and what happens to the entire system when one of these components has problems. So like, I'm kind of making this analogy that like chemical engineering is to site reliability engineering as chemistry is to software engineering. And you can kind of look at like what a traditional engineer might look at, which is process flow diagrams. And in site reliability engineering, you look at system architecture diagrams to understand the entire system. In chemical engineering, you look at like these individual units like storage tanks and distillation towers and separators. And in SRE, you look at these components like caching servers and reverse proxies and application servers. And kind of the thing I'm most interested in today is control systems. In traditional engineering practice, like mechanical engineering and chemical engineering and aerospace engineering, you're interested in like what happens when you control the system, when you turn a knob dynamically, or due to feedback or something like that. How does this influence the entire system? And this is kind of what load balancing is often about, where you where you're trying to like govern how the entire system works in kind of one of these large-scale computer systems. So like a control system in chemistry might have to govern something like this, and chemical engineering might have to govern something like this. So an exothermic reaction is a reaction where you take A and B and you produce C, and you also produce heat. And heat tends to make reactions go faster. And if you have more heat, the reaction goes faster, which means you have more heat. And if you let this thing kind of spiral out of control, you have an explosion, right? Because things get faster and faster and faster, and the temperature goes up, so things expand, and then all of this is happening in sort of an enclosed container, things blow up. And kind of one of the jobs of the chemical engineer is to make sure that this doesn't happen. And this is also what, the analogy of this is a cascading failure in computer science, where you have a failure in one domain that, through positive feedback, creates failures in other domains. So like, usually these types of failures happen laterally. Like you have a failure of a single machine that causes other machines that are similarly configured to fail. That's typically what I'm looking at here. I'm not looking at systems that fail because like maybe you push a bad configuration file and things start failing because it doesn't process requests successfully or something like that. I'm more talking about systems where like you have a domain that fails, then that causes other similar domains to fail. By the way, if you guys have any questions about like any of the terminology or anything I use, just let me know. So like something I might look at as an SRE is a system that looks something like this. So I have clients, and the service I run consists of 6 instances, and I want and the service is implemented in all of these 6 instances. They're all similarly configured. And what I want to do as an SRE is make sure that the service is reliable, even in the face of some unreliability caused by perhaps any of these instances. So what I want to do is have, if instance 1 over here fails, I want the load of this instance to go to these other instances, right? I want to balance the load among all of the healthy tasks, right? I don't want to just blindly send requests to this instance, even if it's unhealthy. So in order to make this reliable, I can either treat a failure of a single instance as like 1/6 of my requests are just going to fail permanently, which is probably not good, or I can fail over those requests to a different instance. So I can do load balancing to balance the load among the healthy ones. Yeah, so like instance 1 goes down and the client starts sending 1/6 of the requests among all of these other 6 instances, perhaps. But in reality, oftentimes you have instances that are behaving slightly differently. They're performing at different levels. Like maybe these instances are machines, and machine 4 over here is on a machine that happens to be scheduled with, or instance 4 over here is on a machine that happens to be scheduled with a bunch of other work, and it's slower than other ones. Or maybe these are different clusters, and instance 4 over here is in an older generation hardware cluster or something, or maybe it's got a bad hard drive, and slow hard drive somehow caused the machine to behave worse. Whatever the case, oftentimes you wind up having slightly different performance levels on different instances in the cloud, in production environments. And if you do something like increase the load slightly, in this case, you might have a case where instance 4 actually gets so much load that it starts to fail. It might even do something like memory exceed. Like it runs out of memory and it can't handle any more requests and it crashes. Okay. So what happens? Well, we said what we're going to do is we're going to take all the load that went from this instance and spread it among all the other ones. Okay. So by doing that, we actually make everything a little bit hotter. And maybe we make instance 1 here a little bit too hot, and it also memory exceeds. Okay. So, well, we're going to apply our algorithm again. We're going to say, let's take the load that went from instances 1 and 4 and spread it among all the other ones. Yeah. Whoops. Right? We kind of broke the system, right? Because we were trying to make the system more reliable, we actually made it less reliable. And so, maybe at some point instance 4 comes back, it restarts, it schedules on a different machine or something like that. But really, these 2 instances are trying to take the load of 6, right? They're taking 3 times as much load as they normally would, and they don't really have a chance, right? If these guys died when they just got 20% more load, there's no chance that they're going to survive if they get 3 times as much load. So everything goes down, and your service is now unavailable. So let's say you're on call for the service, right? Let's say you're a site reliability engineer and you've got the pager. What are you going to do? Well, first you're probably a little confused because everything's memory exceeding and you don't know exactly why, right? I kind of explained to you what happened, but that's kind of a view of things after the fact, after you sort of understood what's going on. But oftentimes when things memory exceed, like maybe there's a query of death, maybe it's caused by, somebody pushed a new configuration file and that causes people to use more RAM or something like that. Trying to figure out exactly what happened is oftentimes really difficult in this job. So maybe what you do is you decide, well, I'm going to add more capacity, right? I'm going to try to fix this problem. I realize it's a capacity-related problem, and so what I'm going to do is I'm going to add more capacity to fix this, right? Ultimately, this was a capacity-induced problem, so adding more capacity should help, right? Well, let's look back at this. If I add a 7th instance over here, what's going to happen? Same thing, right? It's going to get all of the load because it's the only healthy one, right? So it gets all of the load and it dies. I add an 8th instance, same problem, 9th, 10th, right? I can keep adding instances, but nothing's going to fix this, right? Maybe I'll get lucky and multiple instances will all come back at the same time, and things will recover, but by and large, the way you fix this is not by adding more and more instances. So really the way that you sort of fix this problem is maybe you add a little bit of load, but you have to cut off all of the requests entering the system, right? So that, you know, all of these instances have a chance to restart, recover. They don't get all of the burden of the requests that are coming in, and, you know, they have a chance to, you know, start serving requests at a low rate, and, you know, recover. So you basically have to cut off all load, and maybe this happens naturally because people give up on your service. That's really bad, but, you know, maybe you know, maybe you have to do this in some other way. Maybe you have to control it at the client level or something. Okay. So like, let's say, you know, you've had this pager and you fix the service. The next thing you want to do is you want to do a postmortem. You want to understand why this happened so that it doesn't happen again. And you want to come up with some future prevention steps so that, you know, again, you don't keep having these types of problems. So we sort of understood what happened. These healthy servers became lasered to death with all of the load, right? We had we presumably added more instances to the system because a single instance wouldn't be able to handle all of the client load. And then we sort of regressed into a state where like we had a single instance receiving all of the requests of the client, and that just wasn't something that they could handle. We entered kind of a different serving modality where there was a self-sustaining, you know, positive feedback loop of failure, right? And it probably required some sort of human intervention to fix. And because humans had to be involved, it probably took a lot longer to recover because humans are slow. Right? They'd have to understand how the system worked and do something in order to fix it. And usually when humans have to be involved to fix something, you know, good luck. So why did this happen? Well, we had this, you know, one of the things you want to do when you're looking at kind of these failures, if they've happened to you, is look at something from a lot of different lenses. Like try to figure out what happened from different angles and see if that's the correct way to look at the problem, because there's different, you know, each of those different ways you can look at a problem result in different ways you address them. So one lens by which you can look at this problem is that it was actually caused by the health balancing, right? This balancing on health is what caused the system to have this failure spread, right? When instance 4 went down, we decided to send load of instance 4 to other servers, okay? And we could choose to turn that off, right? The conclusion of this would be turn off this health balancing. But that's probably a bad idea because you want to do things like be reliable in the face of a single instance failure, right? So maybe this isn't the right road to go down. Another way you could look at this problem is we just got too much traffic and we didn't really properly capacity plan for it. So we could do things like have better capacity planning to address this sort of problem, but ultimately, like, it's really hard to predict all of the scenarios under which you can get a lot of load. Like, if we want to provision the service such that a single instance can go down, it could be the case that, you know, well, and in order to do that, we need to provision for like 2,000 QPS of capacity. Maybe there's an instance where we wind up going to like 3,000 QPS of capacity because we're like this back-end service and other clients are using us, and it's hard to sort of predict why clients are going to use us. Or maybe we have a really successful launch, and we didn't really predict that it would be so successful, and because of our own success, we wind up having a failure like this. Like, there are a lot of scenarios under which you get much more capacity than you anticipate, and it's not really, you know, it's not really a satisfactory answer to say like, well, we're just going to do capacity planning even better next time to prevent this sort of problem, right? That's not really a satisfactory way to solve this, I would argue. I would argue that the problem that happened here, like the root of the problem here, is that the instances died when they ran out of capacity. When an individual instance had problems, it stopped participating entirely. Like, what it stopped doing anything useful. It just was like, I give up. I'm not going to do any work when I'm overloaded, right? It's better for it to do some work than no work at all. And as a result of it not doing any work, that load went to other parts of the system, which then also had problems. So how are we going to prevent this? Well, there's this thing called graceful degradation. And what this sort of comes down to is you shouldn't try to handle every request, right? There's a limit. And once you get to that limit, do what you can, but don't try to do any more. So don't try to handle all the requests that you possibly could get, because ultimately there's a point where you're gonna fail at doing that, right? It's like, as an engineer, I can't do everything, right? I have to pick what I want to work on and try to do that well rather than try to do everything. And I'll do everything poorly if I try to take on the world. If I try to do every single thing. Load testing, is kind of how we're going to validate that this works. So like we want to validate that ultimately when we send a server more requests than it can handle, that it doesn't die. So kind of a simple algorithm for graceful degradation is you just limit the amount of concurrent requests that a server could handle. So like maybe you say a server can handle 50 requests at a time. And as soon as we get that 51st request that it's currently processing, actually just reject it, right? We're not going to handle that 51st request. Tell the client to go buzz off, tough cookies, there's nothing we can do. We have to figure out what that number is. We have to figure out what that magic 50 number is in order for us to balance performance and stability. And the way we do this is with load testing.
Does the client have to send the request again if they want to let the 50 first?
So you can do things like have the client retry.
Okay, retry.
I'll get into that in a little bit because it's that brings its own set of problems. But yeah. Yeah, so like when you do this testing, there's a couple of things that can happen. You can see the server like memory exceed and just die. It can maybe see that it's performing really badly and just kind of give up, and maybe think it's in like a deadlock or something, or maybe actually does get into a deadlock and just internally suicide or something. It can go unhealthy to the load balancer, so the clients might just stop sending in requests. It could start failing health checks or something. All of these ultimately result in kind of a server that takes itself out of participating from receiving work. And what happens is the servers oscillate between healthiness and unhealthiness, right? They oscillate between doing work and not doing work. And if you go unhealthy to the load balancer, it means that you're either serving your 100 QPS or you're serving nothing, right? And you're unhealthy for a while, you're healthy for a while, you serve your 100 QPS, and then you go unhealthy and serve 0. And this is really kind of a bad behavior because it also means your neighbors start picking up the work that you were supposed to do. You can start serving requests poorly, like have your rate of successful requests drop due to like garbage collection, or you can start serving with excessively high latency. But what you really want to do to actually make the system reliable is fail requests, which sounds counterintuitive, but what you want to do is ultimately when you start getting more requests than you can handle, see some requests fail, right? So like if a server can handle 100 QPS and you give it 120, what you really want to see is 100 QPS succeed and succeed quickly, and then see 20 QPS fail and presumably fail quickly. And you can also do more advanced things like serve lower quality results and maybe serve requests in a cheaper way. That's kind of a more advanced thing. So like, let's say this is what you see when you do load testing. Your x-axis here represents the amount of work that you're giving the system, and your y-axis represents the amount of work that was either successful or unsuccessful. So like, this is the rate of successful requests. As you add load, it's initially successful, and then it reaches some point where it starts failing requests, and it plateaus at 1200 QPS successfully handled. That's ideal, right? At some point, we reach our limit, and we don't start failing any more requests at that point. Our rate of good throughput succeeds, or our rate of good throughput like plateaus and doesn't get any worse as we add more and more load. More realistically, like it kind of tapers off because the rate of successful requests starts dropping because it takes some work to reject requests, and your rate of failure kind of goes up. But oftentimes you end up seeing something like this, where you sort of reach a point and then boom, everything crashes and burns. And that's really catastrophic. So, you do this for a number of reasons, but one of them is to have productive discussions. Like, you can have database discussions rather than opinion-based discussions about like why things are failing, right? Like you can say, you've hit 1500 QPS and the system fails. That's not something that really is, really creates a stable system. You can understand the system better, so when these latent bugs hit, you can, you can kind of debug them and diagnose them. And you can find new bottlenecks, like you know what's happening at the point at which it breaks. It's also important to keep these testing environments realistic. Like you can do things like test on some small segment of production if your failover works really well, or you can try to replay transactions that you've seen before so that like it's representative. But it's oftentimes really, really hard to get this exactly right. Another thing people oftentimes do to avoid problems is they do retries. So what this code basically says is if there's a failure when we talk to our backend, retry it up to 10 times. And let's kind of see what that happens. Let's kind of see what happens in a real system. So like, let's say your backend can handle 1,000 QPS, and your client's issuing 1,100 QPS. If you don't have retries, what happens is you serve 100 QPS of errors, right? Assuming that your cost of rejecting the request is nothing. Okay. But if you do this like 10 retry thing, what happens is, well, you send 1,100 QPS, 100 QPS of that fails. So then you're actually issuing 1,200 QPS. But if you think about it, that 1,200 QPS is actually going to be sent down to 200 QPS if that's going to fail. You're actually having 1,300 QPS of requests. And actually, it sort of converges to the point where you're really issuing 5,100 QPS, right? You're actually only sending 1,100 client QPS, but with the retries, you're actually issuing 5,100 QPS. So your query factor has increased by a factor of 5. Even though you're only 100 QPS, even though you're only 10% over your limit, right? So this, and this is assuming that the cost of rejecting the request is 0. It gets much worse if it isn't 0. So retries can really destabilize systems. And what you should really be doing in those cases is thinking about how you sort of bound this positive feedback. Like, consider things like a retry budget where you're only going to retry 10% of your requests rather than, an unbounded number of requests. Another fun thing that people often do is they like retry they have like a front end, a back end, and a database, and they'll retry between their back end and their database. And then if we run out of retries and we ultimately fail the request to the back end layer, what does the front end do? Retries the request to the back end. So like, if you have your back end retry to your database 10 times, and your front end retries to your back end 10 times, well actually your request is really being retried 100 times at the database layer. Right? And that can really destabilize systems. So yeah, kind of to summarize things, you should really recognize that systems have limits, plan for them, degrade properly, think about defense in depth. Like, you might have multiple internal components and you might expect them to be well behaved, but oftentimes like there are failure modes that maybe you don't anticipate. Think about making sure everybody understands how these failure modes can possibly manifest, have good capacity planning and so forth. And really I think one of the most important things is to really test your assumptions, because you might think that a system behaves in a certain way, but reality oftentimes differs from your expectations. And with that, I'll open it up to questions.
So So the way you get feedback from the instance is through retries. Is there other feedback mechanism that you get that an instance could have possibly failed? Or is there testing within the instance?
So what a lot of systems do is they have like an out-of-band health checking thing. So like you have like 6 instances and maybe you health check this one and you health check all of them, like maybe you look through like the TCP channel to see if it's open or something like that. And you just pick ones that are available. Not sure that fully answers it though. Is that?
Yeah, I think because the question I had was, what happens if each instance finishes processing the request? You can still send, if by 1,000 you finish 900. I mean, it completed 100. So when you do the retry, it goes and hits your 1,100, right? The QPS that you send in. So are these requests do have an expiring time of expiry?
Yeah. So like, one fun thing that can happen is like you have like a deadline associated with the request. Like you want it to expire after 5 seconds or something like that, and your backend processes it in 5.1 seconds. Right. That oftentimes happens when you get overloaded. Like you take a little bit longer than the client expects, and so then the client just throws away all the work. Right. Like you did that work almost for nothing, because if you're expecting it to finish in 5 seconds, and the backend takes 6 seconds to process it, and it responds to the client, well, the client's already kind of forgotten about you. So like, this retry scenario I was talking about earlier, this is only if the backend is really, really disciplined and says, no, I can't handle this request, and only, succeeds once it's only handles the request that it possibly can succeed. If it gets to the point where the backend doesn't actually have any of this behavior, the minute you go to 1,001 QPS, the system can totally fall over. If you have this sort of thing where like the deadlines get exceeded.
Number fail, it just fails for that new request and not for the existing request.
Well, if it then does something like retries that one that went over the deadline, then it increases the load a little bit, and then so now it's at like 1,002 QPS, and then 1,003, 1,004, and it goes up, and this sort of thing oftentimes happens very quickly, like on the order of seconds. So you don't actually notice like the system is like, and then, right? If you look at a graph.
On your testing, your load testing you brought up, you mentioned optimistic versus pessimistic. How pessimistic do you go in order to balance it? And then the other one I had was on your traffic, because you mentioned traffic replay, which is a pretty common one. But nobody has homogeneous traffic. So
yes.
do you work on the mix of heterogeneous in your traffic as like one case? Because that one knocks us over occasionally. But I'm kind of curious about like what are your strategies? Yeah,
that's what gets really tricky. I think I try not to be as pessimistic as possible, but I try to like if you have 5 different clients, I'll do things like only use the worst client in one example, or just try each of the 5 clients in different scenarios, because oftentimes it's the case that like client A is going to bound us on memory, and client B is going to bound us on CPU, and client C is going to bound us on file descriptors, and it's really hard to sort of predict these things. So breaking it up by client seems to work if you have like heterogeneous clients, but it's really kind of an art to make this work very well. And there are other more advanced strategies you can use for load shedding that maybe don't require as many magic numbers, like the 50 number that I was talking about. I can talk more about those afterwards if you're interested. It's pretty advanced. I could go on for probably half an hour about that.
So I have 2 basic questions. One is you must have some kind of fault tolerance scheme in place. So can you expand that? Another thing is monitoring. You mentioned something about it can take really fast for it to suddenly come up with the traffic. But do you have something like monitoring if it hits to say 80%? Is it normally hit 80%? What kind of monitoring mechanism do you have?
Yeah. So there's a couple of different things you can do in monitoring to make this more apparent. For example, with retries, you should be looking at like the ratio of requests that were retried versus, requests that that succeeded, or that were like the initial attempt. Like sometimes you have ballooning in requests that are due to sort of natural behavior, and sometimes it's because the client is just, encounters an error and then retries. In terms of like, monitoring systems in general, like I think it makes sense to like see, to know what your bounds are, like if your bound is CPU or your bound is RAM. This is the type of thing you should be looking at regularly and like maybe be alerting on if you're close to it. Another thing you can be doing is monitoring the rate of, if you actually have this load shedding, this kind of throughput control, you can do things like monitor the rate of rejections due to what looks like the system, like to measures that look like the system's overloaded. So like if you're monitoring on, or if you're rejecting requests once you get to 50 in-flight requests, you should probably be alerting if you're at like 40 in-flight requests, right? Because you're probably pretty close to the limit then.
Wouldn't there be something like an automated instance spinning up? You say you get called in to manually start these up. Wouldn't you like spin up more instances when you hit 80%?
Yeah, you can do things like spin up more instances when you hit 80%. Sometimes it's too slow for it to really work. And if you have something like a caching system, you might do things like invalidate all of your caches and constantly be playing catch up. Like if you go from 10 instances to 12 instances of something like an memcache, you might invalidate 20% of your keys, and maybe you have such a high cache hit rate that that's really bad for you. And so like as a consequence of that, you like need to expand your usage more and more and more, and you don't really know when to stop.
So we have to stop now because it's actually over time. Let's give him a pause.